Okay, so let's talk about the multi-component system. So far, I have talked about polymer dispersity, polymer shape, such as a Gaussian coil and the random walk model, and how to characterize solution, polymers in solution using different techniques. And then I talked about glass transient temperatures and the thermal analysis techniques, amorphous semi-crystalline polymers, and ESC. The only thing that I left is a mechanical property, which will be I'm doing in probably in the next time. But this time I decide to put chapter 18, which is a multi-component polymer system. So multi-component polymer system is in the textbook, and it's many of the textbook there is because polymer material science or chemistry design is very limited by the available numbers of monomers, because if you want to develop a new material, you have two different methods. One is hard way, which is developing new types of monomer, and then develop new types of polymerization chemistry and trying to optimize the molecular weight and molecular weight distributions and to achieve the desired property. That's hard because you have to really start from everything from scratch. The other way is, what about if I have a polymer, one is actually too hard but brittle, and the other one is a little too soft and flexible, but not as rigid as the other one. If I combine those two, can I have something like a property halfway in between, or it's kind of the synergistically combine those two properties? So people trying to come up with this idea about, let's do the multi-component polymer system. The most common one is a polymer blend. So polymer blend is, people typically write it as an A over B blend. And for example here is, if I draw this, so this is a polystyrene blend with, this is a methyl methacrylate. Okay, they're trying to blend these two and to see if they can have a property halfway in between sometimes. And this is not just a demonstration of the example, but later I'm going to give you a more realistic example in the bottom shown up here. But as an example, people using this AB blend. And what about the block copolymer? And block copolymer is essentially A block B, and that's the case. So in this case, you have a polymer A covalently bonded with a copolymer B, whereas this one is polymer A is just blended with the polymer B. Okay, so the constraint for them to have a covalently bonded is a block copolymer. So the chemically speaking, for example, this is a polystyrene. People make the polystyrene first, and then at the end of the polymerization, it has to be a leaving types of polymerization. From the chain end, you start to grow another blocks of polymer chain, which is MMA. And let's say M. Okay, so in this cases, you have a polystyrene block with MMA. So even I can try to make the color. So polystyrene block with MMA. Okay, so they are the one. And in this case, this polymer AB blend, they'll have phase separation. Phase separation at a larger scale, typically very large, tens of micron scale. So that when you have this polymer blend, what used to be a polystyrene is transparent, PMMA is a plexiglass is transparent. You blend them together, you have this very turbid, phase separated one, And so that's why that is not going to be useful because optical appearance is one of the criteria. So they are. That's why there's not many AB polymer blend pairs are used in the industry. It's just an idea about combining the properties of A and B. But now here is an example of A and the B. And in this case is, although A and B, styrene and MMA, like to phase separate into its own aggregated domains, they cannot because they are essentially bounded by this chemical joint, right? So this polymer chemical joint, they are essentially bound by this. So because of that, they just have to just align itself to minimize the unfavorable contact between A and B. And this one, in the polymer community, people call this one as microphase separation. But in a strict sense, this is a polymer that is only one simple kind, though this is just a polymer is an amphiphilic nature of A and B. So it is people later instead of using microphase separation, which is a small scale phase separation, they say order structure. Okay, and the size is in order of nanoscale. Do you remember the radius of gyration polymer, depending on the molecular weight? That's usually 5 nanometers, and this is a 5 to 10 nanometer length scale phase separation is pretty common in block polymer. So those are the example of multi-component system. And then one third one is, if you think about it, how about combining the property together? Can we do the random copolymer? Random copolymer is A random B. Okay, this one is no phase separation. It's just a homogeneous, no phase separation material. So it is, in a way, multi-component, but you're getting the. For example, the glass transition temperature halfway between following the Fox TG blended TG equation or copolymer TG equations. There are other types of another one, which is also we call the graft polymer. It's just a name based on the architecture design. Graft copolymer means, let's say you have an A, but your pendant group B is kind of grafted from. Onto the polymer backbone A. So that's the graft copolymers, and those are the ones. In this lectures, I'm going to focus on give you more details on polymer blend and block copolymer system. That's the one that is pretty well understood here. Okay. So the idea is, can you take advantages of both components at the same time to develop a new properties, and obviously the composition, when we call the FA, fractional composition, and this is essentially molecular weight, Na plus Nb. That's a composition plays a role to define the property of the material, and then what is called the interaction parameter, and we call this the chi, and the chi is in the interaction parameter chi, and this is a measure of degree of dislikeness. Okay, a measure of thermodynamic measure dislikeness. Okay, let me just leave it that way. And composition, and then I guess the total number of molecular weight, Na plus Nb, And that's the total molecular weight. It's also somewhat related to the entropy term of the system. So those are the something that is related to the phase separation of the system. But you're trying to really make, for example, the hard, brittle, and also the soft and flexible, but stretchable material. Can you combine those two to maximize their mechanical properties? The blending is easy to be done, but phase separation is a problem. And the block copolymer is a good idea to link them together, but to making the block copolymer is not trivial. You need some advances in leaving polymerization technique. And I think the Dr. Baez's class, I hope he talked about the leaving polymerization technique, such as an anionic polymerization, that's for sure, and then also leaving radical polymerization, such as ATRP and raft polymerization. So I want to actually continue to a little bit here, and here's give you an example of what is called the high impact polystyrene. Okay, HIPS is an example, and this is a picture of the SEM picture or transmission electron microscopy picture of high impact polystyrene here. Okay, this is a stained one, and the one that's shown up is dark phase is a polybutadiene, and the one here is polystyrene. The polybutadiene is CH2, CH double bond, CH. It has a more complex structure, but mainly it is actually 1,4 polybutadiene is one is a rubbery particle, okay, rubbery domain, and TG around here is, let's say, minus 60 degrees C or so. And polystyrene is a glassy, and then this one is but glassy means polystyrene known to be a glassy but brittle. Okay, it's a glassy brittle polymer, and the glacial temperature is about 100 degrees C. And so this is an example of HIPS. HIPS means high impact polystyrene. Okay, that's what HIPS means, and people are using this the HIPS to have has an enhanced impact strength compared to the brittle glassy polymer. So this is another example. This is a picture, figure 18.1. This is an immiscible blend of engineering polymers with high temperature elastomer. And so this is essentially, I guess, a soft domain. And typically this is a hard matrix. These are the typical idea that people trying to improve by dispersing the softer domain. They can essentially improve some kind of impact and the flexibilities or toughness of the materials and so on. And so this is the efforts. I would like to spend a little bit of the time to explain the high impact polystyrene. How this is being made. The way that it's actually being made is in the reactor. Okay, they are putting the styrene monomer is polymerized in the presence of polybutadiene. Okay, so polybutadiene itself is a rubbery, just a kind of gooey, liquidy material. You just put them in, and then essentially polybutadiene. 1,4-butadiene dissolve in styrene monomer. It's like in this case, styrene almost looks like a solvent here. Okay, so that's what you looks like, and then you start to heat it up. Okay, you start to heat it up and adding the radical initiator and then radical polymerization. And then that's first step. The second step, polystyrene is being formed in the presence of the polybutadiene, right? So in the reactors during by polymerization. Because the polystyrene and the PS and the polybutadiene is incompatible, they phase separate. And depending on how phase separation occurs, and then this is the structure that you see. By controlling the relative amount of polybutadiene, you can have those. One thing that I like to actually give a little bit more elaborate discussion is on this. If you look at this, the structures of butadiene, it's almost like a little bubbles of bubbles, right? You are seeing the even this is a polystyrene, and the dark one is a polybutadiene, and the region is this is actually much more complicated process than just simple phase separation. And I would like to make a little comment on that before I close this session. So during the polymerization, actually polystyrene radical is grafted onto polybutadiene, because polybutadiene, as you know, it has a CH2, CH2. That's a polybutadiene, has this double bond, and they can essentially have a polystyrene chain can graft it onto this. And once you form that, it's almost like you are making this amphiphilic molecule graft to copolymers, right? So then it's almost quote-unquote surfactant. So being produced while you are undergoing the polystyrene polymerization, and so they are making this this kind of morphologies, developing the extent of the ratios and how fast the polymerization occurs and how do you shear the sample and so on. Okay, so why, and the HIPS is high impact polystyrene is a small polystyrene area that people are using it. And why do they use it? Because of, as the name suggests, HIPS means enhanced impact strength, right? So it has the good thing, enhanced impact strength. But what are the downside of HIPS, HIPS? It becomes turbid, right? So it becomes a turbid. And so it's, in other words, not clear. I think one of the main reasons that people using the polystyrene is due to the optical clarity as an amorphous polymer. But start to putting the rubber particle, you can have a gain in the you can remove the brittleness of the polymers and increase the impact strength. But at the same time, there's a price that you pay because of phase separation. And if I blow this one up, this one is, I think, in the scale of a 10 micron or something in that. The scale by here must be something like 1 micron or something in that regards. And so therefore, it is a pretty big, large particle, that rubbery particle that has a different refractive index. They can scatter a lot of light. Okay, so polymer blend is a good idea, but you have to always think about the incompatibilities of the polymers, because most polymers are incompatible, and due to that, most of the cases blend is not so useful. And HIPS is one of the clever idea is actually by grafting the polystyrene radical during the polymerization process, they can actually maintain some phase separate structure for as it is. So that's why there are people using this as an example of material.